are going to be taking JUPEB lecture on mathematics. So this is going to be a week-long series, and I'm going to be your instructor for maths. So hopefully at the end you would have been able to gain necessary knowledge to be able to, sit down for your JUPEB maths exam and be comfortable while writing it, if not aces, without having to stress. So without much ado, we'll begin. We're already behind time, so we'll just begin straight up. So for this week, I'm going to be focusing on foundation of numbers and sets, as you can clearly see in the subheading in the first slide here. So by the end of this lesson, what we hope to achieve is that you will be able to identify real numbers and their categories, which include integers, rational and irrational numbers. Also, you'll be able to perform the basic operations that have to do with real numbers. You should also be able to understand and apply set theory. So, like it's shown here, we're dealing with foundation of numbers and sets. So it's a kind of a two-part topic. So there's also sets involved. So you should be able to understand and apply set theory, everything that has to do with sets, operations, laws, diagrams. And then, of course, as an addition, prove the basic statement using mathematical induction. So at the end of this lesson, if you have not achieved the things that are listed out here, then of course there's going to be time for Q&A. But then this is what I hope to achieve at the end of this class, and then hopefully we are going to see that go to the end. All right. So first slide, number sets. So we are dealing with numbers, right? And then for those of you on this call, I'm just going to ask you a rhetorical question. Now, I'm going to answer the question myself, but then it's just to pick your brain a little bit. When we talk about numbers, right? So if you remember how you were taught growing up right from primary school, there was a point where your math teacher would tell you 2 minus 5. And the answer to that question was, it cannot go. I'm pretty sure we all have some memory of that, right? 2 minus 5, it cannot go. Or, a smaller number minus a bigger number. And it didn't work. You couldn't do it simply because that was what the teacher told you. And then eventually you got a higher level, and then another teacher now tells you that, oh, 2 minus 5 can actually go is minus 3. And then you not get exposed to the number line, and then you start seeing that they are negative numbers and they are positive numbers. And you're like, oh, wow, wonderful. There was a point where you would do square root of 9. Oh, 9 is a perfect square. You get an answer 3. Or you do square root of 2. More. 2 is not a perfect square. So you leave it there. You just write the 2. But later you now realize, oh, there's a way to break this down. There is surds, there's irrational numbers, there's all these things. So, of course, the point I'm trying to make is, as we have progressed in our knowledge of math, we have become introduced to newer and newer concepts. And of course, these things are not things that have been invented. It's just that for the levels at which we were given the information that was necessary, the knowledge that was necessary to, for that particular stage, and then you get exposed to the higher things that you go higher. So in dealing with numbers, there is a wide array of distinctions. There are a wide array of number sets, and of course, this is what we are going to do. This is what this first slide, which I am on currently, talks about number sets. So there are different classifications of numbers, and each of them have their distinct characteristics. So first of all, we have natural numbers, right? So so for those of us on this call, it would be wonderful if you have something to take down notes with. First of all, for reference purposes, because I will have to confirm if the slides can be made publicly available at the end of the class. But simply for reference purposes, I mean, I like to have my own private notes, and as well. And of course, if you during the course of the class have any questions that come up, you can just write them down, and then because the Q&A is going to come at the end, I don't think I'll be taking questions on anything. So you can just write them down, and then you don't forget them. At the end of the class, we'll have a 30-15-minute period where we take questions, and then you can shoot. So back to the slide. So the first one is natural numbers, right? So basically what that means is numbers that you use to count in everyday life. So you go to the market and you tell the woman selling mangoes. Mangoes are in season now. You tell the woman selling mangoes, madam, give me 5 mangoes, right? Madam, give me 2 mangoes, 3 mangoes. These numbers are what we refer to as natural numbers. You count with them. You can't go to the market and tell the woman, madam, give me -2 mangoes. The woman like, hello, Or you can't tell her, give me 2 mangoes. That doesn't make any sense. Or give me, you get my point. But so the numbers that you count your money, you count 1K, 2K, 3K, 4K, 5K. You count, things that you play with in real life. So those are what we refer to as natural numbers that you count. And then it should be obvious what the examples are, right? 1, 2, 3, 4, 5. But of course, we have a table here with the examples. So for natural numbers, we have basically positive numbers, right? Excluding 0, obviously, because 0 is nothing. You don't count 0 mango. There is no mango, there is no mango. So positive numbers on the right hand side of the number line. So those are natural numbers. And of course, the next is prime number. So we know what prime numbers are. This is, from secondary school, we've been exposed to all these things now. Natural numbers greater than 1 that has only 1 and itself as factor. So numbers that fall under this category: 2, 3, 5, 7, 11, 13, 17, and so forth. So those are prime numbers. Numbers that have only 1 and itself as a factor. So these things are important as well in dealing with math, because you are trying to build the concept, right? So that when you come across this thing, it's very easy for you to just, okay, I know that, I've seen that before, and this is what you can do. So composite numbers are numbers greater than 1. So they are natural numbers greater than 1, which has more factors than 1 and itself. So every other number, every other number that is not a prime number falls under a composite number, basically. So for from 1 to 10 now, we have 4 is not a prime number. So you can say 4 is a composite number because it has 1 as a factor, it has 2 as a factor, and it has 4 as a factor. So you can use simple elimination to find the examples for those composite numbers. And of course, we have them in the table here. So 4, 6, 8, 9. Of course, all these that are here are not prime numbers, and so they fall under composite numbers. So the next thing we have is whole numbers. So this is the set of natural numbers with the number 0 adjoined. So remember when I was giving the definition for natural numbers, I said 0 is not included because you can't count a 0, right? So it's either something is there or it's not there. Don't count a 0. But then the whole numbers now is the set of natural numbers plus 0. So pretty much the same thing. So yeah, that is the set of whole numbers. And then the next one is the set of integers. So for those that are not been following, we're talking about number sets and the different distinctions between numbers. So now we're on integers. So now integers are a set of whole numbers, right? With their negative numbers adjoined. So like I said from the beginning, we have a number line, right? We have positive numbers on one side, we have 0 in the middle, and we have the negative numbers on the other side. So now from 0 to positive infinity is the set of integers. It's a set of whole numbers, right? So if you now want to consider the set of integers, you now consider the entire number line from minus infinity to plus infinity. So we are thinking about whole numbers now. So obviously, decimal numbers and fractions don't fall under this set because they are not whole, right? Wonderful. So of course, it goes without saying we should be able to deduce examples of those. So negative numbers, positive numbers, all fall under integers. Fantastic. So the next one we're going to be looking at is rational numbers. Now, this is where we get into the real stuff. Rational numbers are numbers that can be written as fractions. So now we're dealing with decimal. We're dealing with half, quarter, 1/3, 1/8. So numbers that can be written as all those decimals, things that are not whole. So those are rational numbers. And we will see why they are called rational because of their counterpart, which is the next example, is irrational numbers. So of course, rational numbers include the set of integers and then now include the decimals and the fractions. So there's kind of a progression where, like I said, whole numbers, the integers is whole numbers is natural numbers at 0. Integers is whole numbers and the negative. The rational numbers now is integers and then the fractions. So you see a kind of, the next one is swallowing up the other. It's one is a subset of the other. Now, we'll get to that point later, but I just want you to follow it like this so that you understand how this set is about. Wonderful. So I think someone's mic is on. Could you kindly turn that off? I'm getting a feedback from your end. So but then I hope I'm being followed. I don't know if you guys can turn on your mic, but hopefully you can hear me. So continuing, so now we have irrational numbers now. So the difference between rational and irrational numbers is that irrational numbers cannot be written as fractions. Now, what do I mean by that? A very common example is pi, right? So if you try to write out pi, of course, we know that pi is 2/7. But what we mean by kind of written as fraction is that if you try to divide that, the fraction pi, or for example, a sword root 2 goes on forever. There is no end, it keeps recurring. So basically, irrational numbers are all those fractions that have no, that cannot be resolved. So that's where the word comes from, irrational. Something like root 2. It doesn't make any sense, right? You can't, of course, and that's why you were only exposed to something like this at a very high level. Because if they start telling you root 2 or pi or this is when you were from the littlest level of math, you get confused. So the examples for irrational numbers, as we can see here, so we see pi, the first one, we see 0.122, this should be root 2, it's probably a typo, it should be root 2. So those numbers that have that cannot be resolved on a normal level. So, for example, if you want to resolve a sword as a fraction, you have to do something like multiplying the sword and all those resolutions that we were taught. So this is there's an irrationality behind them. And so I'm trying to explain the root of the word so you understand why we have that term, irrational numbers, right? So I hope that's understood. And then the last set is the set of complex numbers. Complex numbers are numbers that can be written in the form of a plus bi, where a and b are real numbers and I is equal to -1. Yeah, wonderful. So of course, the set of complex numbers. So this is where you now have you start seeing strange things like letters in math. And like, yeah, we used to use only numbers before. Now you're introducing letters and it's getting complex. But yeah, I mean, so these things were necessary for math to advance to where it had gotten to now. And of course, someone has to introduce complex numbers. So where you have roots of negative numbers. So we know that for complex numbers, we have letters are used to represent either I or J. So if you have root of -1, so most textbooks will use I, some textbooks will use J, but conventionally, either one can come up. So for a complex number, the square root of -1 is I or J. So I'll just use I for conventionality's sake going forward. So complex numbers, for example, root of -1 is a complex number, which is I. So if you now have root of -2, it will be 2I, right? So you see combinations of an integer and a complex number, and both of them, that whole is a complex number simply because of the attachment of this complex number to it. So the example I have here, 1 plus 3I is a complex number. -3 plus 2I is a complex number. And of course, these things have their use cases. There are places where they will be introducing, of course, in real life calculations as well, where you have to solve for laminar flow and things that involve linear calculations. You see these things coming into play, but this is just the basics, right? Understanding, because you will come across these things in your exams and all those things. So understanding what each of them are and knowing how to identify them when you come across them. So of course, the table, the next slide has been used to explain the previous slide. So these are the examples and of the various number sets that you can have. So I hope that has been able to clarify the different types of number sets we have, and you should be able to identify when you see which and know, okay, this is a whole number, this falls on a set of integers, this is a real number, and like such and like that. So I think I did not talk about real numbers. Okay, so yeah, I skipped real numbers. So real numbers now, and of course that is the next segment we're going to go about. So I mean, it's fitting that I talk about it last. So real numbers is now said that is a combination of rational numbers and irrational numbers. So this is like the umbrella where all of them fall under, of course, excluding complex numbers. So real numbers. So any number you can think of now may fall under this real number as long as it does not have a complex number I, right? So pretty much anything, your fractions, your whole numbers, negative or positive, irrational numbers, all of them fall under the set of real numbers. And of course, we use real because the value of root of -1 is called an imaginary number in a sense because it's not a figure, it's an abstraction, right? It was invented to make calculations easier. It's imaginary. So that's where the opposing term, real numbers, now comes from because these are numbers that you read that you can work with, right? Be it fractions, positive or negative. But then when you now enter the realm of complex numbers, you start to work with an imaginary figure in a sense. So I mean, it's just the basics, right? It's just to know that these things exist and you will come across them. So having talked about that, we move on to the next slide and we see the classifications of real numbers. So of course, like I said, it's the umbrella. So we have under real numbers, we have integers, we have the rational numbers and the irrational numbers. Of course, if you remember, I said a few minutes back, the integers are every single whole number on the number line, negative, zero, and positive. Key point, whole number, negative, positive, and zero. Then the rational numbers are numbers that can be expressed as a fraction, a over b, where b is not equal to zero. Because that's the condition, because we know that anything over zero is undefined, it's infinity. Then irrational numbers cannot be expressed as a fraction. So I can give an example of root 2 and pi as well. So these are the sets, these are the number sets, the relevant number sets that fall under real numbers. And it's important to know this as well, because when we now get into set theory, you would see these distinctions. You would be forced to understand, okay, is this under the set of real numbers? Is this under the set of natural numbers? Is this under the set of whole numbers? Is this under the set of integers? And all whatnot and all whatnot. So it's important to be able to familiarize yourself with these distinctions now, so that when we get to that point, it will be very much easy to flow and understand. So of course, we have our number lines, which I've already mentioned, which can help you to know the positions of your real numbers, rational. So of course, the number line we are used to is very straight number line that has positive whole numbers on the right, zero in the middle, and then to the left negative whole numbers. But of course, each of these other number sets can find their positions in the number lines. The only difference now being that they will be inside all those other little spaces. So if you have 0, 1, 2, 3, 4, when you now introduce a set of rational numbers that are fractions, you'll be having 1 over 2 somewhere between 0 and 1. You'll be having 5 over 4 somewhere between 1 and 2. You'll be having 9 over 2 somewhere between 2 and 3. So of course, the spacing is no longer going to be even as integers are, but then each of these number sets can be represented on number lines, and then that's the point of this representation. So moving on to the next slide now, we are going to talk about the properties of real numbers. Of course, it's another important aspect to look at, because when you begin to do your operations with real numbers, when you begin to calculate, when you begin to, try to manipulate these numbers, of course, it's important in math. You need to know what can happen in each situation. You need to know the properties, and we'll see why that is important in a minute, because these things are things that are going to come up regularly and are going to aid you in making your calculations and your work easier. All right, so let's get right into it. The properties of real numbers. So the first property we have is the commutative property. Now the commutative property has to do with the addition symbol, the addition operation. So it states that for every real number, A, so let's say you have two real numbers, A and B. The commutative property of real numbers is that if you have A plus B, it is the same thing as B plus A. Now, in your head, think of any random two random numbers that fall under the set of real numbers. Just any random two numbers. The commutative property is telling us that if you, no matter the order in which you arrange it, their sum is going to be the same. 1 plus 2, same thing as 2 plus 1. 1/2 plus 3/4 is the same as 3/4 plus 1/2. You know, and like that going forward. So that's the commutative property that no matter the order in which it is arranged, if you have two real numbers, their sum would always be equal, right? Fantastic. So that should be pretty clear. Then the associative property is the next one. So we have in a bracket here, we have A plus B plus C is the same thing as A plus B plus C. So the associative property also has to do with addition. And it tells us that the sum, so when you're working with three real numbers now, for our example, we have A and B and C. It tells us that the sum of A and B added to C is the same thing as A added to the sum of B and C. Now this should be pretty intuitive because addition works very straightforward. That no matter the order in which it's arranged, their sum would be the same thing. Now, this cannot work for subtraction because subtraction is not that straightforward, of course. If you rearrange the order, then your output, your result is not going to be the same. But then for addition, we have two properties which align, which are the commutative property and the associative property. So the order is irrelevant to say the least. So in these examples, we are being shown that when we are working in real numbers, we can reorder them when we are working on an addition operation, and then our output or our result would be exactly the same. Wonderful. So the next property is the distributive properties, and it tells us that A into B plus C is equal to AB plus AC. So it's pretty much like opening the bracket. So here it's telling us that, and it comes from the term distributive, that if you distribute A over B and C, so a multiplication distributes over an addition, it opens that bracket, it shares itself in a sense. So this distributive property tells us that A into B plus C is AB plus C equals to AB plus AC. That's the distributive property. Then the identity property is that A plus 0 is A and A times 1 is A. Now note, these properties apply for all real numbers. All real numbers. The inverse property is the next one, and it tells us that the sum of a real number and its corresponding opposite negative number is equal to 0. And then the multiplication of a real number and its reciprocal. Now a reciprocal is 1 over that number. The multiplication of that is equal to 1. And of course, there's a condition in the bracket where A is not equal to 0. Now that is important because, of course, for the multiplication, if A is 0, then you're going to have 1 over 0. And of course, that is undefined. That cannot work. So the inverse property has a condition that it applies when A is not equals to 0. Fantastic. So these are the basic properties of real numbers which we are going to be looking out for working with when we start to work with real numbers. So it's important that you know all of these things because it's going to be like a shortcut or a guide to the operation of real numbers. And of course, that the various operations are going to be working with real numbers. It's important to also watch out for your signs and your brackets because those things will come in play when you're doing your operations. And then this is also an important aspect to look out for, especially when you now start to introduce other operations that are not very straightforward or don't fall under that this property that we've listed out, right? So a few examples now. So we see the first one, 2 over 3 plus 1 over 6 is 5 over 6. Now, if I were to reorder this and say 1 over 6 plus 2 over 3, it will still give me the same output, right? So another example. So before I go on, I want to quickly point out the different types of number sets we have here. So we see what we have here now is 2 over 3. This is a fraction, right? There's no whole number here. We have 2 over 3, we have 1 over 6, we have 5 over 6. Now, I said that the real number set has all the numbers except the complex number. So pretty much everything you can think of except complex numbers fall under the real number set. And now that we are seeing varying type of numbers, we are seeing sorted, it's an irrational number. And so we multiply two irrational numbers and it gives us what? A whole number. Wonderful. This is a fraction. This is a rational number, rational number, rational number, whole number, integer. This is negative. So we are seeing the different numbers we talked about playing out here in the operations we are carrying out for the real number. And so it's important to be able to identify these things and apply the operations and the properties where necessary. Because it's important to have them in mind. Know that okay, this can work, this and this cannot work. I can identify that this is a real number, a rational number, and know what set it falls under. Now that takes us into the next part of our discussion, which is an introduction to sets. Now, when we talk about sets, when we talk about, I think this is something that we've been hearing right from secondary school, I believe, where we talk about set theory and all of that. So basically what a set is a collection of distinct objects or a group of objects. So think about a what can I use as an analogy now? Think about a class, a school, for example. And so you have a distinction between junior secondary students and the senior secondary students. Now, every junior secondary student falls into one set of junior secondary students. And what makes that a set is because everybody there have similarities, have something in common, right? So from the definition I have here, a set is a collection of distinct objects. So those junior secondary students are different. What makes them different is their position in class. That's what makes them different from the senior secondary students. And the senior secondary students are having their own set of senior secondary students. Now we decided to use this junior and senior as a distinction. We could have decided to use any other thing. We could have decided to use gender, right? We'll have a set of all the boys in the school and a set of all the girls in the school. Or we could have decided to even go class by class. A set of all the GS1 students, a set of all the GS2 students, and a set of all the GS3 students. Like that and like that and like that. But the point is, a set is a collection of distinct objects or a group of objects. So things that are a collective. And so those objects that are formed in your set are called elements or members of a set. So for example, the set of junior secondary school students, if I were to go there and pick out one person in that set, with respect to that set, that person is a member. It's called an element or a member of a set because he was taken from that set. He's inside that set, and so that's the terminology we use to describe. Of course, you should take note of this thing because they will show up when we start to do examples. So on the previous slide, sorry, before I move on, there are different representations for sets. So we have the roster form and the set builder form. And what do we mean by roster form and set builder form? So in the roster form, all the elements of the set are listed, separated by commas, and including curly braces. Now I'll use a different example so that we can bring the point more closely to home. Imagine if I were to say I wanted a set. Now I've described a set as a collective. I told you that I want a set of all the even numbers below 10. What would you do? First of all, I've given you a condition, I've given you a limit. I want a set of all the even numbers below 10. Now, note the wording below 10. So it means that 10 cannot be in that set because 10 is not below 10. 10 is equal to 10. If I had worded it differently and said all the even numbers up to 10, then it was possible that 10 would be in that set. So it's important to also pay attention to the terminology, to the English used, because it can make the difference between your set being correct or incorrect. Now, if I say I wanted a set of all the even numbers below 10, what would be the elements? What would be the members of my set? Of course, we'll start from 2, 4, 6, and 8, right? Because 8 is the last even number below 10. And if you were to represent that set in roster form, it would simply be a, so of course you would name your set, right? You would give it a title or a name or something to identify it. Set of A, set of B, set of whatever, for example. So here in this example, we are the set that is being gathered is the set that represents all the leap years between 1995 and 2015. And as you can see, there are only 4 of such years. And so we represent that set by picking out all the elements. So first of all, you have to find the elements of the set, put it in a curly brace. So this symbol here is referred to as a curly brace, and then use commas to separate the members of those sets. So that's how you form your set, and that's how you represent it in a roster form. Now, the other way you could represent your set is in the set builder form. So in a set builder form, of course, all the elements have a common property. That's the point of a set. It is a collective. You have things that have points in common. And so for here, for the example that's used here, okay, let's reuse the same example. For x, for a set of numbers that are just even numbers below 10, so you would not represent or you would not write out those elements now like we did in the roster form, but you would simply state what you think members of the set are. So in the example I've used here, x and 2, okay, are there even prime numbers? I don't think that's the correct representation. So let's just use the example that I've already started. X is an even number below 10. Wonderful. So this in itself is a set, even though the members of the set are not listed. But then we have some differences. So now X is a representation for the elements of the set that you will list out or that should have been listed out. But now we use a variable to represent it. And of course, this set now is named S. But the X inside is representing the elements of that set. And now when you put that representation, you now write out the condition for membership of that set in a sense. You get what I mean?